Welcome to this side event on what does net zero imply and how can we get there. We have a few speakers lined up for you, all from the Engage project. That's a European Horizon 2020 funded project that we coordinate at EASA. We start with myself, Bas van Ruiven, group leader of Sustainable Surface Systems group at EASA, in a few minutes, given an highlight talk of scenarios to reach 1.5 degrees and net zero in the future. Then we'll have Christophe Bertram from the Potsdam Institute of Climate Change Impact Research to present about the investment needs for reaching net zero. And then we will have Elina Brucien from EASA and Silvia Pianta from CMCC in Milan to present on how to assess the feasibility of climate mitigation pathways that reach net zero. And at the end, we will move into a more interactive session with discussing the feasibility assessment and how to assess feasibility of mitigation scenarios. But let me start first with setting the scene, and you should be seeing my screen now, is what I've understood. Can someone confirm that? Did you see my presentation?
Yes, we can see your presentation very clearly.
Okay, thank you. Yeah, because I wanted to first introduce you to what it actually takes to get to net zero CO2 emissions and why. And if we look at 1.5 degree scenarios and how much CO2 we can still emit until we are at 1.5 degrees, we have historically already emitted, roughly 2,200 gigatons CO2, leading to about 1 degree of global warming. We have some non-CO2 left to be emitted in the future, and then if we want to limit our warming to 1.5 degrees, we have still about 400 to 500 gigatons CO2 left that we can emit until we reach that threshold of 1.5 degrees, or that target of 1.5 degrees. And at the current rate, where we are emitting around 42 gigatons CO2 per year, if we keep our emissions stable, we would exhaust this budget in about 10 years. And so this is the very narrow emission space that we have to limit warming to 1.5 degrees. But scenarios that explore how to limit warming to 1.5 degrees have been rooted in different types of philosophies. And the conventional scenarios that we have seen in the past basically reduced emissions, but allowed for overshooting that target, because the transition comes to steam relatively slowly. We need this massive deployment of supply side options in high demand scenarios, and this overshoot of the temperature target is compensated later in the century by going below zero in our emissions and having net negative emissions through carbon dioxide removal technologies, and reach the 1.5 degree target by the end of the 21st century. We have here worked actually on a different type of scenarios, ones that do not include this overshoot, and ones that actually start on a rapid transformation immediately, mostly, for example, through demand-side technologies or the scale-up of granular technologies, or a very rapid scale-up of other technologies. But this allows these scenarios to reduce emissions quickly in the next few decades and then stay at net zero, and remove the need to go to net negative emissions. So this is what one of a recent big model comparison effort is about. It's a community effort to really better understand how to limit the overshoot. So we have here about 9 models with modeling frameworks from all around the world, and we systematically explore the scenario space for either having a delay and overshoot. You see these red arrows, what happens to CO2 emissions there, or the blue arrow directly bringing down emissions and then having no need for net negative emissions later in the century. And this comparison between overshoot scenarios and scenarios without net negative CO2 emissions is what we try to highlight as in this whole session as a different paradigm. So, for example, if we look at then the 1.5 degree scenarios in this set of scenarios, which are the top graph on the right, we look at the time when net zero is reached for 1.5 degree scenarios here in. Then we see that the blue scenarios, the ones that are not overshooting the target and are going for net zero CO2 emissions, have a much earlier time of reaching net zero than those with delay and overshoot that you see in red in the bar chart here on the right, that generally have a net zero time of around 2070, 2080, whereas the non-net zero scenarios for 1.5 degrees have net zero times of 2050 to 2060. If we look at 2 degrees, the graph at the bottom, we see that's the same, right? That there's a later time period for reaching net zero under the delay and overshoot scenarios, but the net zero scenarios in blue have an earlier moment of reaching net zero. So you need to reach this carbon neutrality earlier if you want to go for these net zero scenarios, and you cannot no longer reach the most stringent scenarios because you're not allowed basically to overshoot and compensate that. However, there are benefits to this. So in the short term, these scenarios require higher investments, higher transformations of the energy system. But if we compare these full century scenarios with these net zero scenarios, and we look at some of the indicators like GDP, we find that later in the century, the net zero scenarios perform better. So earlier in the century, you make this big investment, and you have a bigger drop in GDP, but later in the century you benefit because once you have gone through the transformation, you're in a low carbon society that does not need to further remove carbon from the atmosphere. But net zero means net zero across different sectors and across different regions. And if we look for individual sectors, which we do here in the graph on the left, for one particular pathway, you see the black line depicting the total CO2 emissions, which indeed go to net zero in 2080 in this particular scenario. But you see that energy supply in red and afforestation and land use in green are going negative and below zero CO2 emissions, so are removing CO2 from the atmosphere earlier and keep doing so later in the century. Whereas other sectors, which are harder to abate, like transport, buildings, industry, keep emitting CO2 emissions, and which are then compensated by the power sector and land use. And this, if we look to the top right graph, here we see how the different models that are in this model comparison study have their positive and negative emissions across sectors divided. And you see that this picture is relatively stable, that the power sector, the energy supply sector, and the afforestation and land use sectors are the ones that are removing CO2 and compensating for emissions from transportation, buildings, industry, and mostly those. Except for with the exception of just a few models where other sectors can go negative as well. If we look across these different sectors in the bottom right, the timing of net zero, we also see that land use emissions are the first ones to go below zero, energy supply follows, and then the other sectors are either not or very late going towards net zero as well and being compensated. And a similar story emerges across regions. This being completely from the technical side. There's no no effort sharing or ethical considerations in this. This is just where the economic potential is to reduce emissions, and it does not include who actually is paying for them. But if we look where the emissions are being reduced, you see emissions being reduced overall, but going negative in Latin America especially, but also in the OECD regions that have potential for carbon dioxide removal technologies, whereas other regions like Asia and the Middle East and Africa are staying above zero and are being compensated then by the regions that are going below zero. And you see this emerging on the top right again for all the models in this study. With their different strategies, consistently across all of the models. You see always Latin America going negative. Sometimes also the reforming economies of the former Soviet Union, and also the OECD and EU negative, and others like Asia, Middle East, Africa staying positive. And that is also then reflected in the timing of net zeros, of going net zero for individual regions. Latin America goes first, reforming economies and OECD follow, and then Asia and Middle East follow later, if at all. So that's what I wanted to tell you about this set of scenarios that we have developed and that we elaborate on in our session today, especially now with Christophe Bertram going into the investment needs on the short term for these, for reaching net zero under these scenarios.
Yeah, thanks, Bas. Let me quickly share my screen, and then directly continue, and kind of the presentation that you just gave is an excellent introduction, as it kind of presented already the core kind of logic of these so-called net zero budget scenarios that we analyze in more detail in this study. You see here that this study, which is part of the ENGAGE project, was published last month in Environmental Research Letters. So you see the link with the DOI down there, and you see that it's kind of a huge group effort, just as the paper that Bas just presented. And the motivation for that paper is to look into detail of how kind of ambitious peak warming targets kind of imply specific action for the next decade, and especially kind of the investments in the energy system that are required for the next 10 years. In that sense, it's kind of a follow-up paper to McCallum et al. In Nature Energy, but importantly, we kind of have a few innovations that really kind of make kind of an added value here. And on the first hand side, it's a similar set of models that we are using, but we make sure that the power system configuration and also the capital cost assumption for key mitigation technologies are really calibrated well to match observed values in the year 2020. And in that sense, kind of really make sure that the near-term realism of the scenario is higher than it used to be for some of these models in past scenario exercises. And then the second core innovation is what Bas really introduced very clearly with these blue curves that really decisively limit the net zero cumulative CO2 budgets. So these budgets from 2018 until the point of reaching net zero CO2 globally. And we look at these either with immediate action starting after 2020, but we also in some of the slides look at delay scenarios where kind of countries only achieve their pledges until 2030 and ambitious climate policy kicks in unanticipatedly only thereafter. And to contrast these kind of ambitious scenarios where we really kind of scan the range from 400 gigatons to 3,000 gigatons, we contrast these also with these more exploratory scenarios that look at if we kind of extrapolate ambition of NDCs or current policies, so NPI, what would result in terms of warming, but also what kind of would be the consequence for investment in these kind of scenarios. So the first the first figure, kind of, it's important to kind of understand well how kind of these x-axis works here. So this is really what has been kind of harmonized across models that we kind of scanned this range. I said kind of with the one model reaching 400 gigatons CO2 emissions from 2018 until the point of net zero. So as Bas just said, it would imply basically having 10 years of constant emissions and then directly falling off to zero, or kind of more realistically, kind of having a linear decrease in 20 years to net zero. So this is very ambitious end of the spectrum. And on the right-hand side, 3,000 gigatons until net zero basically mean that very, very likely, I mean, you consume this by not reaching net zero in the 21st century. And on the y-axis, you see kind of how the median warming at peak level kind of results from these CO2 budgets. And you see there is some variation across models, and Bas already mentioned these non-CO2 contributors that play a big role there. But you see very consistently that there's this clear, nearly linear relationship between the peak warming and this net zero budget. And this is kind of why in the coming graphs, you will always see these net zero budgets on the x-axis as you see here. And you can kind of keep in mind that this basically relates to the peak budget with the peak temperature level with the lowest temperature on the left-hand side. So here showing the carbon prices that are required to limit the peak temperature to these levels. And you see that kind of with increasing policy emission, the carbon prices really escalate. There's some deviation across these 7 models shown here. But what is quite interesting is that if we now contrast these immediate scenarios with scenarios where there's a delay of policy of 10 years, so following NDCs until 2030, and then only then afterwards increasing policy stringency, we have this very consistent shift to the right of all these curves by roughly 400 gigatons. And this kind of adds roughly 0.2 degree peak warming, but then is kind of inevitably added to the peak warming level that we can observe. And yeah, just to kind of put your attention to the left-hand side where we kind of here define these colored areas for a potential interpretation of 1.5 degree scenarios with limited overshoot and well below 2 degree scenarios, ranging until 600 gigatons and 1,000 gigaton net zero budget, respectively. So now, if we want to get into that range, what has to happen until 2030? First kind of indicator that we look at in detail here is the CO2 emissions shown in gigaton CO2 per year on the y-axis. And for reference, the dashed line indicates the level of 2019 global CO2 emissions. And the first thing you note, the x-axis is as it was before with the addition of these NDC and NPI scenarios on the right-hand side. And you see that with these current policies and the slight increase of ambition with the stated current near-term target level, emissions wouldn't substantially change in the next 10 years. But if we, in turn, want to reach very ambitious long-term temperature targets, and especially kind of limiting the peak warming level to 2 degrees in this kind of a darker green shade, or even close to 1.5 degree peak warming, indicated by this brighter green shade, or you see that in order to stay on track for reaching these peak warming targets, there really is not much leeway possible anymore. And all these scenarios that kind of enter the brighter green area kind of roughly halve emissions in the next 10 years. So in order to decompose how this roughly halving of emissions is achieved, we kind of make here a simple Kaya decomposition. On the top right side, you see how energy intensity of GDP evolves, with kind of 1 indicating the 2020 levels in these models. And you see that for energy intensity, there's kind of an autonomous improvement. So all scenarios independent of climate policy stringency reduce energy intensity in the next 10 years. And there's a slight additional effect of climate policy. So you see that towards the left-hand side in these green areas, there's slightly lower energy intensity. And now, unlike the normal Kaya decomposition, we now decompose the emissions intensity of the electricity system on the left-hand side and those of other fuels on the right-hand side on the bottom, and see this clear pattern that in all models, the key phenomenon and the key mechanism to decrease emissions is by decreasing emissions from the power system, with kind of some models reaching close to a decarbonized power system already in 2030. And one reason why this is so crucial is that obviously for some of the other sectoral emissions, one key component is also electrification, and that only makes sense once you are close to decarbonized power supply. So now looking into the investments that are required to bring about this huge shift in the power system in just 10 years' time. Not very surprisingly, investments in key low-carbon power technologies like solar, wind really dominate and really see escalating investment values, as you see here, if you go to these low kind of net zero budget targets in these green shaded areas. As a reference, in each of these panels, the dashed line shows you the 2019 level of investment. So you see that really for solar and wind, but also for transmission and distribution and storage shown on the right-hand side, there's a huge increase of investment flows. Also, the kind of exact magnitude kind of differs across models. In turn, the complete sum of other low-carbon technologies, including nuclear, hydro, biomass, geothermal, and so forth, kind of is also an important contribution and also is scaled up compared to 2019, but it doesn't kind of even combined reach the level of the other components in most models. And in fossil electricity supply, there's this clear decrease. As even including CCS, fossil power generation is only competitive in very few kind of markets. The flip side to these low carbon investment in the power system is how the investment into fossil fuel extraction develop in these scenarios. Obviously, kind of the models don't capture these investments at the detail that would be required as kind of like, fossil extraction is a much more kind of a heterogeneous set of sectors. The representation on the investment side, I would say, is not kind of as good as for power system technologies. But what is kind of important is that kind of the models are good in kind of projecting how different primary energy demands for these fossils develop over time. And I think this is also a key takeaway, that you see this distinct pattern with primary energy demand for coal on the bottom right, really showing this very steep declines in very ambitious net zero budget scenarios in these green shaded areas, whereas primary energy supply for oil and gas kind of has more modest declines. But what is noteworthy on the right upper panel is that kind of there is also a few scenarios from some models that in these kind of 1.5 degree area really kind of can confirm this finding from the IEA that kind of they already put out in last year's World Energy Outlook, but now also highlighted much more in the net zero report in April, that it might not be necessary to invest into any new fields in 1.5 degree scenarios for it. So to sum up, kind of what showing here only the temporal evolution of investment shares in the energy system in 1.5 degree compatible pathways. So these scenarios that have a 600 gigaton net zero budget. And you see that the share of non-fossil investments, which is kind of indicated by these curved lines, across models increases very rapidly. So while kind of these non-fossil investments only represented roughly half of overall energy investments, they quickly increase to 80% in 2030 and keep on increasing furthermore. And you see also that on the other hand, the overall magnitude of investments differs quite a lot. Clearly, there is an increase compared to today's level, but by how much exactly, there's less kind of robustness across models. Another interesting kind of pattern that you see here is that there really is this kind of rush hour for power sector decarbonization, where the electricity sector share of overall investment and also the share of solar and wind really peaks around 2030. And this is kind of the reason for this is that on the one hand side, it's really bringing online new capacities, but also replacing the old fossil capacities in the power system that mostly in these scenarios is mostly finalized in the next 10, 15 years. and therefore afterwards this burden in terms of the investment shares is lower. And the other important pattern obviously here is also that kind of other low carbon fuels such as hydrogen and so forth are kind of at a much less mature state as of today, and therefore the upscaling will require some time, and the bigger contribution in terms of investment will only be seen later on, therefore. Yeah, so as I already used up all time, I kind of just leave you here with the conclusion slide and look forward to some discussions. But first give back to Buzz, I guess, to introduce the last presentation.
Yeah, thanks a lot, Christoph. That was very interesting and clear. And maybe to reiterate, if you have any questions, please post them in the Q&A chat box that you have on the right of your screen. I hope it's also on your right, and all screens are the same. And then we can pick them up and answer them. So that holds for all of the 3 talks and everything that you see here. But first, I'm going to introduce our last 2 speakers, Elina and Sylvia, who will present about how to assess the feasibility concerns that might arise from the scenarios, the type of scenarios that you have just seen.
Yes, I hope it will work with the sharing the entire screen. Okay. And do you see now the presentation?
Yes, that works.
Yes, we see your presentation.
Okay, perfect. So also again, our final talk builds on the scenarios that were presented by Bas and Christoph. And as Christoph has highlighted, one of the main goals also of this project was to give a special attention to the feasibility, so sort of more link it to the real world implementation of the new scenarios. So the major question therefore arises is how to assess feasibility of climate pathways. And in this talk, I present the insights based on an article that was also recently published in the Environmental Research Letters, and here also the list of the co-authors. So what is feasibility of climate pathways? So the scenarios that we have seen in the past 2 presentations are based on the integrated assessment models, which interlink the economy, energy, and land systems, and already are, as also highlighted by Christoph, based or calibrated to real-world data, and basically assess the different pathways that might be feasible to reach certain climate targets. And so what we have as an output are different pathways. So for example, from the ENGAGE project, we have 2 different types of scenarios as clearly explained by Bas. We have the so-called full century scenarios, and as you can see here, sort of a stylized figure, that the pathways go from currently around 40 gigatons CO2 emissions. Up to end of the century, they go some of the scenarios require quite large amounts of negative emissions, which can go up to minus 20 gigatons of CO2. On the other hand, we have the so-called global net zero set of scenarios. And here, as you can see, this set of scenarios does not have global negative emissions. And so this both set of scenarios that we are looking at the so-called 600 gigaton budget scenarios, and as highlighted also in the presentation by Christoph, they reach below 1.5 degrees. So, and what we try to do with our feasibility concept is to assess the plausibility of the transformation required given a particular temporal and geographical context. And maybe just here for a moment, I will maybe let Sylvia take over for a second. Since my daughter is at home and is asking to get something. So maybe I'll be back in a second. Yeah. Apologies.
Okay, now can you see my screen and hear me, right?
Yes, Sylvia, we can see your whole screen, however, so we're seeing a window of a window. Now we can see your whole presentation. Thank you.
Now you
Yes,
see.
wonderful. Thanks.
Okay. So, picking up on where Elina stopped, we developed a systematic framework to evaluate the feasibility of different scenarios, and we build on insights, on the triangulation of insights from the past literature on scenario evaluation, but also on empirical studies on different mitigation options. And we also employ currently available empirical data. And what we try to do is use these insights to evaluate the feasibility of different scenarios across different feasibility dimensions. And we pick up the dimensions developed by the 1.5 report of the IPCC. And therefore, we evaluate geophysical, technological, economic, institutional, and sociocultural feasibility of scenarios, also in order to highlight the possible trade-offs between different dimensions. So some scenarios which might raise very low technological challenges might raise instead high economic challenges due to the economic cost. So what we do is we develop different indicators for each of these dimensions. And each indicator, the value of each indicator in each scenario is evaluated as possessing either low, medium, or high levels of feasibility concerns. And what is really important to stress here is that we do not want to give a binary evaluation of what is feasible or what is not feasible, but just evaluate the levels of concerns based on the current knowledge that we have. And this framework can be updated in the future using different indicators or different thresholds based on newly available evidence. But now we define 3 different levels of concern. A low level of concerns correspond to values of a specific indicator, such as the scale-up of renewables, that has been already observed in the past or documented in the literature. We instead define medium levels of concern as what can be plausibly extrapolated based on current state of knowledge, and instead high levels of concern are like levels that are unprecedented or speculative rates of transformation. And it's really important to stress here that we focus on the required transformation, and we evaluate the required transformations in different points in time. And we can then perform different aggregate feasibility evaluation in a given point in time or across time or for different feasibility dimensions. And one interesting insight that we can take from our systematic evaluation is we can compare the overall aggregate feasibility evaluation of net zero scenarios and full century scenarios. And we can see that the net zero scenarios that are in green in this graph on the bottom right raise higher feasibility concern in the short term, but then present lower longer term concerns, while full century scenarios that do not step up climate action now are less concerning in the present, let's say, but then present higher and more sustained feasibility concerns later in the century. And this is just an example of what can be, how this feasibility evaluation can be employed. And I'm not sure whether we still have time or Elina wants to go with the tool.
Definitely. I think that would be great if you can show some of the tool and then we also paste it into the chat.
Mm-hmm. So I will paste the tool to the chat now. Okay.
So in the meantime, while Elina, okay, she goes.
Yeah, and I'll try again sharing the whole screen. So you see the tool now? Yeah. And
yes.
Yes. And I guess I can guide you a little bit also for the tool. So basically what we would like to show here is also a more interactive way to get to know this different type of scenarios. And so here, I'm so sorry, because we have a shortage of sausage supplies. But yeah, here we have, again, the scenarios that I have shown you before. And here, for example, you can focus also on the net zero budget scenarios, or on the full century scenarios here. I'm very sorry. So, or the full century scenarios. And then, and here.
I can go if you want.
Yeah, maybe it's always when I talk. Yeah, sorry.
Absolutely no problem. So I'm sharing my screen and opening the tool. Okay. So this is what Elina was showing here. So the first tab of this interactive tool allows to see different emission trajectories of different scenarios. But what can be also nice to play with. So please let us know if you're working, like opening the tool and it does not work for you. And in the meantime, I proceed with explaining a bit. In the second tab, which is the indicator-based evaluation, we report a bit here the schema of our framework, of our evaluation framework. But what we allow to do here to the user is to define different thresholds for the medium and high feasibility concerns. So we present here the thresholds for medium and high feasibility concern that we developed for our paper, which are based, as we said, on the triangulation of insights from the literature and empirical literature and scenario evaluation literature. And you can see here in the second graph that we can compare feasibility concerns for full century and net zero scenarios. And here, when the gray color reflects low feasibility concerns, yellow reflect medium feasibility concerns, and red reflect high feasibility concerns. And these colors somehow reflect the colors of the Roma football team, but this was not intentional. And you can see here that if we compare full century and net zero budget scenarios somehow raise slightly higher feasibility concerns in the short term, but then feasibility concerns are relatively similar for full century and net zero budget scenarios in 2050. And what we can do here, we are looking here at the share of renewables, defined as the share of non-biomass renewables in total energy, electricity generation. And we can, for instance, see what happens when we define stricter threshold for the scale up of the share of renewables. So if we think that the transformation in this for this indicator will be harder, we can shift the feasibility concern threshold, and we can see that this somehow changes the evaluation of full century and net zero budget scenarios. But again, here we see that the difference between full century and net zero is higher in 2030, but in 2050, feasibility concerns are more equal. And we can do the same for other key indicators that we provide here. And this is the share of carbon capture and storage as a percentage in electricity generation. And here again, we can decide to define more generous or less generous thresholds for CCS. So for instance, if we think no very low scale up of CCS is possible, this will produce higher feasibility concerns, especially as we can see here in the mid-century. We display in this interactive tool some key indicators. So some indicators are related to technological options, but some indicators are also related to economic costs. And the main indicator measuring economic cost in integrated assessment model scenarios are carbon prices. And here we can see the value of carbon price in net present value, and we define thresholds for carbon prices based on current carbon price levels. So the highest level of concern for carbon price levels is a carbon price higher than $120, because today we have the highest carbon price of $137. And we can see if we allow for higher carbon prices more feasibility concerns decrease here. And finally, another fundamental dimension that will determine the feasibility of different climate pathways is related to sociocultural aspects, and energy demand, and in particular reductions in energy demand, can be driven by different individual behaviors and different scenarios. Let's say only recently reductions in demand as an important mitigation option has been explored, and we can see also here how our evaluation of the feasibility of different scenarios changes if we allow different values of final energy demand reduction. So I don't see you, so we'll go back to the main. Okay. Elina, do you want to jump in somehow?
Yeah, thank you so much for taking over. And so, yes, I guess the main point of the feasibility framework of a method that we have developed is that we have these different types of indicators pertaining to different dimensions. And we have, in our recent article, proposed some thresholds to relate what we observe in scenarios to what we think are the different levels of concern, of feasibility concerns in the real world. So, and we think that this way, this allows us to really see certain key trade-offs in the stylized scenarios, as we have shown, especially over time, that obviously early climate action requires much faster transformation by 2030, and therefore raises some feasibility concerns about the pace of this transformation required, but at the same time, delaying climate action then raises more persistent concerns as the system grows later and requires reliance on some technologies where it's really not clear whether they can be deployed or not, and therefore there's a multiplication of feasibility concerns. And at the same time, this framework is flexible and still in development, so we are really looking forward to get more input also on the indicators, which are more relatable for policymakers, and also more specifically on the thresholds, or how to adjust thresholds as well, so that it's easier to understand also for policymakers, or to add additional evaluations to improve the overall framework, and to manage this link between feasibility of what we observe in scenarios and the real world feasibility. Yeah. And so if you have any questions, please let us know.
Yeah, thank you, both of you. There has been one question actually in the Q&A on the tool itself, on whether one can also see the effect of multiple indicators at the same time, or for the same scenario. And so maybe you can elaborate a little bit on that part.
Yeah. So one part that we have not shown as well in this visual tool, so if you go to the sort of overall or multiple indicators of evaluation, which works best also if you use Chrome as a web browser. So there we have used the so-called parallel coordinates. I'm not sure if it will load now for Sylvia in Chrome. And so there you should be able then to select on different dimensions, and therefore evaluate different indicators at the same time, and then see the set of scenarios that that satisfies your conditions. But as I said, since it's a little bit still under development, the still especially with parallel coordinates part, it doesn't always work. Yeah, exactly. So this one, thank you. And so here, Sylvia, I can show that we have these different dimensions, and here you can also set up your thresholds visually, and then see the set of scenarios that fulfills your conditions. And also, for example, in this tool, we have colored the scenarios based on their share of renewables in 2030 to again highlight a little bit this trade-off that we clearly see between higher and faster deployment of renewables by 2030 versus later deployment of, for example, CCS technologies. So scenarios which are delayed or don't have such a rapid scale up of renewable technology then rely much more on CCS.
Yeah, thanks a lot. Yeah, that is a great summary at the end of the tool where one can look across the different indicators. Let's see, we have another question from Shihari on whether we see the results of the feasibility analysis being incorporated into any of the IEM scenarios going forward, or whether this is more input for policymakers. Well, here you can say that this is basically what the second half of the Engage project is about implementing these feasibility considerations into a next generation of integrated assessment model scenarios. And we have just started the process of, for each of these dimensions and indicators, starting to think about how can we meaningfully impose those onto new scenarios so that we develop scenarios that raise fewer feasibility concerns than the current generations of scenarios. Open question with that still is whether one can actually develop scenarios that raise a very minimal amount of feasibility concerns, or whether in the end we are always trading off one feasibility concern against another, and whether the real world is more about making very tough choices, because it's going to be hard somewhere to do the mitigation and limit warming to 1.5 or 2 degrees, or whether there is the pathway that sort of sails in between all of these concerns, and that will helps us to get to a 2.5 or 1.5 degree world in a with the least upheaval and the least least barriers to run into. I don't see other questions here, but actually wanted to ask one to Christoph first on the feasibility around investments, and where you see whether you think it's feasible, these investments that you've shown in your presentation, in your paper, where you see the barriers for those materializing, also what can be done to to move the trillions, to bring those investments actually towards mitigation where they are needed.
Yeah, super relevant question. So I guess we can basically, for answering this question, very much kind of tap into the framework that Elina and Sylvia have just proposed, and kind of separate the question of the technical feasibility of kind of bringing these investments about. And I think the answer to that question is that this kind of, is like in really plausible ranges, kind of even if you scale up kind of solar and wind investments by a factor of 4 in the coming 10 years, that doesn't seem kind of as something that is hitting kind of bottlenecks on the technology side. I know that there's also quite a lot of investigation into kind of also the material demands for that, and so in that sense, from a kind of a technological point of view, this seems feasible. But obviously, it will not happen just by its own, right? And in that sense, the crucial determinant is whether or not policies are in place to kind of make sure that investments into low carbon solutions today kind of really generate the revenues that kind of pay back these investments plus a small return on top. So that investors really think this is kind of an interesting thing. And in that context, I mean, one thing that is still a big caveat, and obviously also needs to kind of be flagged as a limitation of the study, because obviously we don't look in detail into kind of the regional power market structure that obviously differs across regions, and it's clearly more challenging to bring kind of the right investment shifts into place in non kind of market systems. I mean, it also can be done obviously with regulated market, but kind of this core factor of the price differential really triggering the investment shift as is seen in the model kind of would require kind of market structures. And the other point obviously is, if you have market structures, the question is there kind of any form of credible and predictable climate policy in place? Because obviously that also determines the competitiveness of low carbon. We know that in some places and for some kind of shares and also for some actors, obviously it already is kind of competitive even without climate policy to invest into wind and solar. So think of kind of being a homeowner in many places of the world. It just is kind of an economically rational choice to kind of build PV onto your roof. But the kind of for the amounts of investments required in these scenarios, obviously these kind of competitive investments without climate policies wouldn't suffer. So we really kind of need clear signals from the policy making side that really underpin the medium and long-term targets that are in place by now in most countries. So this is kind of the good thing. But the bad thing is, in many of these countries, these long-term and medium-term targets are really underpinned by current policy that is crucial for the credibility of these targets for long-term investments.
Yeah, thank you. Thanks a lot, Christoph. And with that, let me actually also point people to another side event we are organizing tomorrow at 2:30, but especially the role of the finance sector in mitigation scenarios and how important the finance sector is there. Yeah, maybe one question for Sylvia, while I still highlight that if anyone in the audience has questions, still please put them in the Q&A box. We'll discuss them here. But for Sylvia, in this, when you look into this assessment of scenarios and this multidimensional feasibility framework, what would you identify as the most unexpected feasibility concern that came up out of this work? Something you had not expected before you embarked on this?
Yeah, thanks for the question, Bas. I'm not really sure how unexpected this was, but I think the size of it was a bit unexpected. Like the importance of institutional constraints that we define as like limitations or challenges due to different governance capacities in different countries was very interesting for us. And I think this somehow, so I would add two things to this. Now we perform all this evaluation at the global level, but feasibility evaluation of scenarios can also be performed at the regional level, and we for sure plan to do that. And we think that's really interesting because we see that some scenarios really are more challenging, especially in in fastly developing countries, let's say. So we think looking at interregional let's say dynamics, and also in the future on how what are the enablers that can allow lower feasibility concerns, especially in developing countries. This can be also a very important point. And we think that it's really important to, let's say, increase the communication between the integrated assessment model community and social scientists, because we know much more about technical and economic challenges, and we are starting now to study a bit more institutional challenges, but also challenges due to barrier to behavioral changes and energy demand, but also consumption of high-emitting meat products can be interesting dimensions to look at. And yeah, I don't know if Elina wants to add something.
Yeah, thanks. Yeah, these are all great points. And as Sylvia has highlighted, I think this is the most challenging part, is try to link the insights from political science and the role of policies and institutions with models where it can be done only in a very stylized way. So we are only at the beginning also trying to link this somehow and think how to incorporate empirical insights and into new scenario development.
Yeah, thank you. And with that, I think we're coming to the end of this this side event. We're almost reaching the top of the hour, and many of you have to move on to other sessions. So thank you all for joining. Thank you, all of our speakers, for great presentations. And we hope to see you at some of the other side events that we are organizing, and at the rest of the Vienna Energy Forum the next 2 days. Thank you.